So we have seen Quicksort, which is a divide and conquer algorithm which overcomes the requirement for an extra array as in merge sort. So let's do an analysis of Quicksort. So remember how Quicksort works, right? You pick a pivot element, say typically this first element of an array, okay? And then what you do is you partition this into two parts such that you have a lower part which is less than or equal to p, and maybe you have an upper part which is bigger than p, and you move this pivot in between. And then you sort this lower part and upper part separately recursively, and then you don't need to do any combining step because these two things are in the correct position with respect to each other. So the first thing we observed is that this partitioning actually is quite efficient. We can do it in one scan of the entire array, so we can partition with respect to any pivot in order n time. So the question is, how big are the recursive problems? So if the pivot is the median, then you would expect that by definition of the median that these are of size n by 2, because the median is that element which splits the array into two parts. Those half of the elements are bigger than the median, half are smaller than the median. And if we do have this fortunate situation that the pivot is the median, then we end up with a merge sort recurrence which says that t of n takes time 2 times t n by 2 for the two parts, and this is the partitioning step. So it's not the merge step after the recurrence, but the partitioning step before the recurrence. So we have, as we saw in merge sort, this recurrence takes order n log n if we expand it out. But the pivot is in some sense the best case. What do we think is the worst case? Well, the worst case is when the pivot is an extreme value. It's either the smallest value or the biggest value. So if it's the smallest value, then what will happen is that everything will be bigger than the pivot, right? So you will have an upper element set which has n minus 1 values because the pivot is the smallest value, and you'll have nothing on this side. Symmetrically, if the pivot is the largest value in your array, then you would have everything in the lower element set. So this is again be size n minus 1, right? And the pivot would be something which is on one extreme end and there's nothing in the upper set. So now what we see is that in order to sort this array of size n, I have to then sort a smaller segment which is only n minus 1. It is not no smaller than n minus 1. So I have tn takes tn minus 1 plus n. N is the time taken to partition. And tn minus 1 again in the worst case will have again a pivot element which is an extreme value. So for example, supposing we start with a already sorted array like 1, 2, 3, 4, right? Then what happens is that we pick 1 as a pivot, right? And then this then results in us wanting to sort 2, 3, 4, and then I'll pick 2 as a pivot, right? And this results in us wanting to sort 3, 4, and so on, right? So if I have an already sorted array, in some sense, the pivot is always an extreme value, so the next step splits the array very badly. And of course, if we expand out this tn is tn minus 1 plus n, we get the summation that we got for selection sort and insertion sort, so this becomes order n square. So the worst case of Quicksort is actually order n square, which is the same as the worst case for selection sort and insertion sort. So why do we bother with this much more complicated algorithm Quicksort when we already know several intuitive algorithms which are order n square? So it turns out that Quicksort, we can show, actually does not behave in this worst case way in a very frequent manner, right? So we can actually compute in the case of Quicksort what is called the average case complexity and show that it is n log n. So we will not actually show that it is n log n, but we will try to at least explain what it means to compute the average case analysis of Quicksort. As we said in the beginning, average case is very difficult to compute, so let's see what it involves to do this. So the first reason why the average case is difficult to compute is because we need to have a way of describing all possible inputs. Now, even for a sorting algorithm, all possible inputs is an infinite space. Supposing I just take arrays of a fixed length. Supposing I take arrays of length 4. So I could have an array which look like 43, 12, 38, and then 62. Right? So this is an array with 4 elements. I could have another array of 4 elements, which is say 72, 21, 63, and 95. Right? But in this way, we can continue and put any elements we want, and there are infinitely many arrays of size 4. But there is a commonality between these which says that the first element is bigger than the second element. In fact, the second element is the smallest element, and so on. Right? So if we look at this, we can say that there are four elements, and if we think of them in order, then the smallest element is here, the second smallest element is here, the third smallest element is here, and the fourth smallest element is here. So I can actually think of this as the array 3, 1, 2, 4. It has four elements, and the four elements are ordered in this way. So the actual values are not important, only the relative order matters. So we can actually think of inputs of size n to be these kind of reorderings of 1 to n or permutations of 1 to n. Now among these permutations, we don't have any preference. Any one of them could come as our input, right? So we all know that there are n factorial such permutations, and we say that each of them is equally likely, so each of them has probability 1 by n factorial of occurring. Now we look at all these n factorial inputs of size n and see how our algorithm behaves. So we will not do the actual calculation, but if you see the average, you see the actual time it takes for all these n factorial inputs, add it up and divide by n factorial, which is what is in probability known as calculating the expected running time. Okay, then you can show that this is actually order n log n. So we have not shown it, we have just explained what is the mathematics required in order to show this, but in Quicksort you can prove that the expected running time across all possible random inputs, equally likely inputs, is actually order n log n. So though Quicksort has an O n squared worst case, on the average it behaves like merge sort. And without some of the pitfalls of merge sort, in particular, it doesn't require this extra space in order to create a merged array. Now you can actually exploit this average case behavior in a very simple manner. Right? So why does this worst case occur? The worst case occurs because the pivot that we choose could be a bad pivot. As we saw, if you took the first element as your pivot, then a sorted array becomes a worst case because every time the pivot is the extreme element. On the other hand, you could take the last element and you would have the same problem. If you pick the midpoint, again you can make the middle point of the array that you start with the extreme element, and you can then work backwards and construct always a worst case which takes order n squared. So what we are saying is that for any fixed strategy, if I tell you in advance that I'm always going to compute the position of the pivot in a fixed way, then by working backwards you can always ensure that that position in the current problem, you have a worst case that is an extreme input, and reconstruct something which will take O n square for that strategy. So the solution is to not fix the strategy. Each time I want to apply Quicksort to a recursive subproblem, I have some position 0 to n minus 1 which I need to pick as the pivot. But rather than telling you that it's going to be 0 or n minus 1 or the midway between 0 and n minus 1, I will say that I will choose any one of these values with equal probability. So think of it as choosing a random number between 0 and n minus 1 equally likely. Or if you want to think graphically, it's like throwing a die. So a die has, say, 6 faces normally. So if you roll a fair die, you'll get any number between 1 and 6 with equal likely. So now we have an n-sided die. So we have a complex kind of object, we throw it, and whichever number comes up, we pick that as a pivot. So now the behavior of this algorithm is not fixed, right? It depends on how this die rolls. So this is a different type of algorithm called a randomized algorithm. Right? So you can now implement Quicksort in a randomized way with a very simple randomization step, namely just pick the pivot at random at each call to Quicksort. And it turns out that again you can do a similar calculation saying that across all the possible random choices I make for the pivot, the expected running time is order n log n. So there's a very simple, this is a kind of a dual result to the fact that the average case is n log n. You can exploit that by creating a very simple randomized strategy in order to achieve this n log n thing with good probability. The other aspect that we mentioned about merge sort, which is a bit limiting, is that it's inherently recursive. Now our solution to Quicksort avoids this duplication of space, but it is recursive. Now it turns out in Quicksort you can actually manually make the recursive algorithm iterative. Okay? So the point is that the recursive calls work on disjoint segments. So what you need to remember in the recursive call is not the entire segment, but just what segment you need to work on. You don't need to combine the results. So we will not discuss this in great detail, but it turns out that you can use a stack. You can actually maintain your own stack, and every time you make a recursive call, you just store in the stack the left and right endpoint of what segment needs to be sorted. And in this way you can actually take the recursive algorithm that we wrote before and convert it to an iterative algorithm. Now, why you would like to do this in general is because you have a trade-off in recursion versus iteration depending on your programming language. Because when you make a recursive call, when you make a function call in general in a programming language, what happens is the current function that you're computing has to be suspended, right? So you need to suspend and resume, right? So when you make a recursive call, you have to put aside whatever you have, and then you have to take a new set of local variables. So in the memory of the program, you have to load some new data. Then you have to execute the function. When it terminates, you have to throw that off and restore the context. So you have to resume. So this takes some time and it takes some resources. And so usually the cost of making a function call, even though we might account for it in our complexity as a basic operation, is much more than doing some really arithmetic operation like addition or something. So in particular recursion, every time you make a recursive call, you're basically going and replacing something on the stack with some new frame and then putting it back, and this takes time. So it is in general, sometimes for efficiency purposes, good to convert recursion to iteration. On the other hand, this process can make the algorithm more obscure, and many programming languages actually or optimizing compilers can try to do this automatically. So maybe this distinction between recursion and iteration does not always help so much, but it's useful to know that certain algorithms can be done both ways and certain algorithms is difficult to do one way. So a final remark before we leave Quicksort for now. So in practice, Quicksort is very fast. As we said, the worst case happens very rarely. For this reason, typically Quicksort is the default algorithm that you see that people use when you have a built-in sort function. So if you have a spreadsheet and it allows you to sort a column, then usually the algorithm running in the background to sort that column is Quicksort. Or if you have a built-in sort function, for example, C, C++, Java, all allow you to just call sort. Even Python just allows you to just call sort. In almost any programming language, the sort function that is available to the programmer by just a simple call is usually an implementation of Quicksort. Of course, this implementation may use various optimizations such as the randomization and other things to make it faster. But at the underlying algorithm, the heart of it is usually Quicksort.